So okay, so last lecture was about the composition of subsystems, and I gave you the basic story, I think. But still, there's some practical things that may be useful to know for how to go on. So we had composition. And tensor products. Now, for practical computations with these things, it's sometimes useful to organize your tensor products in different ways. So we had that if, let's say, E mu in H, let's say H Alice, and alpha or so. So I tend to give different basis labels to different bases. So this would be the end of the Greek alphabet, this would be the beginning, and Latin indices or whatever could also be there. This helps a little bit to keep track of where you are. Right? So these are bases. Then these product vectors. Sometimes write this for shorthand are a basis for the tensor product. So the labels for this product basis naturally form an array as well, right? So alpha runs over some range and mu runs over some range. So actually the natural ordering of the basis vectors, well, there is no natural ordering, right? So the natural ordering is in an array. Now, for practical linear algebra, meaning numerical, practical linear algebra, we need to organize this in a organize this. Well, need to order this. So, although a program like Mathematica can handle higher order tensors. If you have an operator on a tensor product space, so this naturally has 4 indices. And if you want to compute the eigenvalues, for example, Mathematica will, well, deny that service, certainly, because all the linear algebra routines are for 2 tensors, for things with 2 indices. So you have to turn these 4 indices into 2 indices, basically by ordering this array, finding a numerical ordering in that array. Now there are 2 obvious choices. One is row by row and the other is column by column. And actually these correspond to taking HA tensor HB or HB tensor HA in some sense. Right? So the tensor product operation, composition of 2 subsystems, is an intrinsically unordered operation. Nobody tells you if I put a proton and an electron together, it should be irrelevant. It's a matter of choice whether you put the electron first and the proton second. In your, let's say, in the usual way, it would show up as which is the ordering of the arguments in the wave function. You can do this either way. It clearly doesn't matter, right? But so you have to make a choice here, and so typically by row, and then your indices would run like 1, 1, 1, 2. Let's say, well, let's just do the simplest case. Right. So this could be your tuples of indices. And then if you have a matrix, it would be organized into a block matrix, right? So let's look at how different operators look at that. So if you take a tensor 1, this would be something that is diagonal in the second index. So if you just change the second index, or if the second indices are different, this is going to be automatically 0. Right? So now here you have an element where the second index differs. So this would have a 0 there. And here also the second index differs. So you have a 0 there. So you have something diagonal here. And the same is true in each one of the blocks. Right? So, and actually you have matrix elements for that, and you just, what am I, is that, yes. So this is A11 times the identity in the second argument. Right? And here you have your A12, A12, A21, A21, A22, A22. Right? So this is what a tensor product with the identity would look like. And the fact that you have an identity in the second part means that each of these blocks is proportional to the identity. If you have a 1 tensor B, how would that look? So how do you recognize a 1 tensor B operator? Same thing, you have these blocks. And, well, in this case, the first index is relevant. So if the first index differs, and the first index is 2 in this whole block, and the first index is 1 all along here, so then you would have a big 0 there. And so where are the B indices? B, yes. So you have just the matrix B here. And the second time with the same matrix elements here. Because this is a feature of the identity in the first factor. Okay? So recognizing these patterns will be a useful thing. So if you, I can maybe do one more example. So if you have these thinking in terms of block matrices is often useful, right? So if you have, now I have so the operators on the tensor product. These are spanned by the product operators, which means that this is also a tensor product of these vectors, or of these operator spaces, and so I can, if I introduce a basis here, so these operators would be a basis. First one was late Greeks, so this would be mu. Okay. So these form a basis in this operator space. Of operators. And therefore, if I have any element of any operator on the, or let's say x or something, if I have any operator here, I can expand by choosing a basis in the first factor. So x can be written as a sum of a mu and nu, then these operator tensor something that is left in the second argument. Right? So every operator by definition can be written as a linear combination of simple tensors. Now, each one of the factors that appears in the first part can be expanded in this basis. I do that and collect the corresponding terms from all the terms in the possible sum. So every operator can be written like that in a unique way, where so x mu nu is an element of the second. I think I haven't introduced these basis kets explicitly, although all the bits there were introduced. So these are bras and kets with respect to the basis. So what is this kind of operator? That is the operator that has a 1 or a matrix. As a matrix, it has a matrix exactly where the first in the muth row and the nth column it has a 1 and everything else is 0. Right? So this is the natural basis in which to expand operators or expand matrices. So it's like the basis that has a 1 in one position for a vector and zeros otherwise. Right? So like that's a canonical basis for Cn, and in a similar way we have a basis for the operators, and it's naturally written like that. Right? This is a useful way to write the basis. So this is what I used here, and so these will be these are the blocks, or the other way around. Yes, these are the blocks. Yes, this way around. And one of the simple things here is what happens if so I can think of an operator on the tensor product space as a matrix where the indices of the matrix are the basis indices of the first factor, and the entries of the matrix are elements of the second observable algebra. Right? And the multiplication rule here so if I take the product of x and y has a similar decomposition, right? Then I have a sum of nu for x and a sum of, let's say, nu prime. So I can compute that, and we learned last time that these product operators are multiplied factor-wise, right? So this is equal to, so I multiply the first factors, so this gives mu prime, tensor x mu nu, y mu prime. Right? Now I can do this sum, or I can actually simplify this, because this factor here, that's the basis, right? So this is delta mu prime. I can replace the mu prime by nu. So this is the sum of mu and over, let's say, mu prime. Then I can put a sum here of the remaining index, that used to be nu, x mu, x mu, the y, mu prime. Okay? Now, I've reorganized the sum a little bit. I mean, the sum could be outside as well. Right? So I've moved the sum in to emphasize that this is actually xy and the matrix element mu prime. You recognize the formula. This is how I multiply matrices. This is exactly the formula for multiplying matrices. And when the space HB is one-dimensional, and that is operators are one-by-one matrices, that is numbers, this is exactly the product of operators written out, expanded in a basis with respect to the first factor. Right? So this is exactly the product formula for matrices. So xy is multiplied by writing the two things next to each other and summing over the adjacent indices here. Right? This just comes out of the simple tensor product formalism. And but the interesting point here is that x and y are now matrices themselves. So this is a rule for multiplying matrix-valued matrices. Now, in this case, it's very relevant whether you write xy or yx. These don't commute. So you just have the rule for matrix multiplication. So if you want to multiply operator-valued matrices, so when the entries are themselves operators, that's basically what we're doing here, then everything is just the same, only you have to pay attention to the ordering of the factors, and this ordering of the factors has to be the same as here. Okay, so organizing operators on a tensor product is something that will come up repeatedly. So, incidentally, if the second factor is maybe not a matrix algebra, but some other abstract algebra, for example, a commutative one for a classical system, this works in exactly the same way. Right? So we'll use that in a little while to discuss how to do the tensor products for hybrid systems that combine classical and quantum information. And this story will be exactly the same. As long as the first factor is a full matrix algebra, I can do this expansion. Okay, so let's come to the next section. What did I have numbers for that. 114. So we had maybe a 0-1 result. So we had a way of graphically representing a basic experiment with a preparation and a measurement. Right? And this is the simple measurement that only gives 0-1 result, but it could be something else. Now, but very often we are interested in doing something to the system on the way. So this is prepare, operate, do something to the system, and measure. So this is a slight extension of the scheme that we had before, and of course this happens all the time. Right? So if we're talking about information processing, clearly the operations, what we do with the system will be described in terms of these of some transformation here. So mathematically this is given by a state or by a density operator. This will, the term here is a channel, and the term here is, I don't know, an effect or observer. So how do we mathematically represent channels? Huh? So now Now, there are two ways of doing that. By using we have this basic formalism of Hilbert space, density operators, and observables. So how do we fit these channels into that? Now, typically, the Hilbert space might even change by this transformation. For example, the transformation, so the Hilbert space H in could itself be a composite. So there are two systems that we're actually feeding to the channel. And we are making a measurement on one of them and doing something to the remaining partner depending on what we measured. So then, of course, the system that we measured on is no longer present in the output. And therefore, the Hilbert space can actually change. So this happens all the time. Right? But how can we describe this? Well, this is really just an experiment that follows the pattern that we had before, and there are two ways of making it look like one. And so one, let me draw the two separately. Right? So I have to repeat this picture. So here's one way to look at it. So we made a preparation, and then we measured something on it. The measurement is a composite, though. It has a T and an F part. But the whole thing together is supposed to be just another measurement. Right? So this whole thing gives us a 0, 1 output, so there's nothing special here, and we call this effect T of F. Now, F would be an element of B of H out. I'll probably soon drop the ins and outs here, but okay. So this is and this is in B of H in, because we're considering this as a measurement on the input system to the channel. So we have that T is a map from B of H out to B of H in. Okay, there's another way to look at exactly the same experiment, and this is just by doing the grouping differently. Right? Nothing much happens here. So we can do the grouping like this. Now the picture is different. This used to be in the trace class of H in. Right, this is a preparation of the input system, and this whole thing is now so call this T star rho. And this would be in the trace class of the output system. And then this is just computed like a trace. Right? So we have this map T star is a linear map taking T of H in into T of H out. Well, strictly speaking, it needs to be defined only on the density operators, but then I can make a linear extension of that. It certainly has to be an affine map, that is, convex combinations of rows have to be the convex combination has to go through. Why? Because a convex combination is a mixing operation that has nothing to do with a quantum system here. Right? So we would just choose different experiments by a random generator, and according to that choice, would prepare different states. So this is how we make a convex combination. Now if we do that, we would just have separate experiments and combine those by the same weights, by the same random generator decision, so that at the output we would have the same thing. Right? So I could preface this with a box choosing which row to take, and that would be exactly the same operation on the other level. So it's clearly it has to be a linear map, and there is an equation. So actually this whole thing is called the Schrödinger picture. Of a channel. And this whole thing, let me write it underneath as well. This is called the Heisenberg picture of the channel. And there's an obvious identity that tells us that we are really just talking about the same thing. And that is saying that the trace of T star rho, I omit one set of parentheses here, F. Now this trace is a trace in H out. Right? So just to emphasize that, let me write H out here. So this is equal to the trace. Now this second trace will be an H in, because I'm looking at it in an experiment on this kind of system, T of F. Or T, let me be consistent, I guess. Let me emphasize it like that. So, as usual for linear maps, I don't write the argument parentheses. I did here, right? So this is the application of a linear operator on F. This is actually an operator on operators. Some people call that a super operator, but it's still just an operator, right? So I definitely, only when I really want to emphasize that point, I would maybe say super operator. So, but this is a linear operator, so typically we just don't write the parentheses when we act with a linear operator. Right? So this is what I did here, but the brackets here emphasize that this is one object, this is another state, and this is just an observer, and it's like here. Right? That's just another effect. Okay, so this very deep equation, the identity, the equivalence of the Heisenberg and the Schrödinger picture, that's what this is just saying that we can regroup in different ways, and it's always the same experiment. And it looks very much like taking an adjoint, right? So we have something like a scalar product here, and there as well. And we have a linear operator, and we can make it act on one side or on the other. So this is like an adjoint. It actually is an adjoint in a slightly more general setting than we are used to. So there's not the Hilbert space setting, but a setting of Banach spaces. So there is a Banach space of trace class operators for each of these. T star acts on that. The dual space of that is the space of bounded operators, and that is the space of continuous linear functionals on the trace class, is the bounded operators, and the evaluation functional for this pairing is given by the trace. So then it exactly is a case of taking the adjoint. So T is actually the Banach space adjoint. Okay. And because the bounded operators are the adjoint of the trace class, but not conversely, these are infinite dimensional spaces, and these spaces are not reflexive, that is, the second adjoint is not the space itself, but a larger object. It makes a difference which one is the adjoint and which is the space and which is the dual space, and therefore I sort of write this as a pre-adjoint. So the star is at the bottom. Right? This equation shows my preference for the Heisenberg picture, because the Heisenberg picture doesn't have an additional notation, but the Schrödinger picture does. Right? Now, that's a matter of taste. So in the quantum information community, the dominant taste is largely writing everything in the Schrödinger picture. Why? Because it sort of follows the systems. You have a state and you operate on it, so you get a new state, and so on. Whereas the Heisenberg picture, you see here, it's a map from the, oops, where is it? It's a map from the output objects to the input objects. There's nothing deep in this. Just think of this grouping. Right? It's obvious that it has to be this way. Right? But, so this is a little bit like inverse Polish notation. Do you remember that? There used to be pocket calculators that had a stack, and you would just write stack operations. But you would sort of write the operations after the operands, and well, it's a little bit like thinking backwards. Now, it's obviously equivalent. The two ways of writing things are equivalent, and we will see that sometimes one is better than the other. So I propose as a notational scheme, knowing myself, I would usually write things in the Heisenberg picture and put a star when I want to emphasize that we are now thinking about the completely analogous object in the Schrödinger picture. But I might actually also just work in the Schrödinger picture and put a star on top if I go to the Heisenberg picture. So the letter, depending on the context, right, I would say what I think it will always be clear which of the pictures is meant. Now, how did this appear in your quantum mechanics lecture? Definitely, people there also talk about the Heisenberg picture and the Schrödinger picture. And they usually do this for one very particular channel, which is the time evolution. Now, the time evolution is just one of those operations. And it goes like this. You make a preparation, and the system that you prepare has a natural intrinsic dynamics given by the Hamiltonian. So you make your preparation, you wait for 10 seconds, and then you make your measurement. And this waiting time in between, where you let the system evolve according to its natural dynamics, is the channel. Right? Just letting it run is the channel. Right? And if you apply that to this case, then you see that you could either think of your channel as a modification of the measurement that follows, or you can see it as something that is done to the state. Right? And these two ways of thinking about it are definitely the same. So one thing that we learned is that every channel can be represented as a map as a super operator, right? As an operator on operators taking stuff on the output system to the input system. So I think this is a time to erase. Huh? It doesn't really make sense to split these, does it? It gets nasty. So Okay, so let's adopt the Heisenberg picture for the moment. Everything, of course, goes completely analogous in the Schrödinger picture. So this is a linear operator. And of course, we need to fix some properties of this. Now, so definitely necessary is that if f is positive, f is in H. Why did nobody protest? I gave a whole long speech about how these are ordered. Nobody. Okay. So the necessary condition clearly is that f is positive and maybe less than 1. So it's a possible detector operator giving a yes/no output, right? Then it must be that T of f is also such a yes/no measurement. So in particular, if we scale that with a factor, we have that if f is positive, it must follow that T of f is positive. This is an important part of this condition. So we say to this that T is positive. Now, positive is a word that appears all over the place with different meanings, right? So here it means that applied to a positive object, it gives a positive image. Right? But it turns out, and we'll come to that, it turns out that this isn't quite enough. So actually, what we often want to do is parallel processing. So again, you have your basic experiment. Okay. And suppose that actually we had something else. We had H by. We had another system, and our initial preparation was actually a measurement. Was a preparation of two such systems, and maybe also our measurement is one that somehow involves both systems. Right? So this is a slightly modified experiment using a channel T, but here's also what I call an innocent bystander. Or in German, ein unbeteiligter Zuschauer. So here we have another system, and we're not really operating on that. This could be on another planet, right? But our initial preparation was such that it produced a pair of the H-in system and some bystander system. Now, this whole thing should still be a legal operation. So, and this is definitely what we do in quantum information all the time, that if we want to decompose, let's say, a big quantum computation into steps, then the interesting decomposition is one where each of the steps refers only to a few of the quantum memory cells and leaves the rest alone. Right? So this is a very typical situation in information processing, that you may be operating on a subsystem. Now, each one of these, this could be a preparation that is more complicated than just the tensor product. We will talk about entanglement at quite some length, so I should say it could be an entangled system here. And then, of course, this way of operating on a subsystem should still be well defined. So the representation of this is a tensorization, well, I call this, I move this a little bit, H bystander. And here is an empty box. And this is the identity that does nothing to any system. And this whole box here is then described by as identity tensor T. So just to make sure, this is the third level tensor product that we have now. Right? So it's possible to get confused. So there is a tensor product at the vector level. Right? This is a tensor product corresponding of Hilbert spaces, and the typical elements in that are tensor products of vectors. Let's write those in white. Right? And then there is a tensor product of operators. This is one level up. Right? Let's write those in red. And now we have a tensor product of superoperators. So let's write those in green or whatever. I don't care about the colors, but they're different objects. So this is very much like object-oriented programming. Right? Tensor knows what it's supposed to operate on, or gets that as part of the information. And we definitely have three levels, and they have nothing to do with each other somehow, except that the definition always looks the same. Namely, this is a level 3 tensor product. So what does this do to a level 2 tensor product? Well, guess, right? It does this to that and that to this. Right? So this will be a tensor T. Right? So, but this corresponds exactly to this experimental situation. When we test this by maybe product preparations and product measurements, doing nothing is indeed represented by this kind of tensor product in such a setting. Right? So id is the operation from B of H so id from B of H bystander to B of H bystander has the property that id of A is A. So this is the identity operator. I do distinguish between the identity map on operators, so the identity superoperator, I write this as ID, and the doing nothing on a vector, which is an element of the observable algebra written as boldface 1. So this is not the same as that. This is the identity superoperator, this is the identity operator. I'm just telling you these trivial things so you find it easier to keep track of what I write on the board. Right? So with this distinction, I'm fairly consistent. And okay, so what we are seeing here is a necessary condition for a channel is that it has this property. But we want more. We want that this still holds for such a combined composition. By the way, this also automatically also means that we can tensor, that we can do operations in parallel, non-trivial operations. Let's say S and T. Why? We are just splitting that into identity tensor T and S tensor identity, and then just multiply with an obvious rule, then we get S tensor T. Right? So if the critical thing to look at is that identity tensor T is still a channel. Right? So what we require, therefore, if F is in the bounded operators of Cn, some Cn, some finite dimensional system, tensor H out. Right? So now it's an operator on a larger system. I've extended the system. So the H bystander actually here becomes an n by n quantum system. Right? It's enough to take that. We'll see that this is enough. Right? So, okay, so if this is an operator and f is positive, then it follows that int tensor t applied to f is also positive. And we, so of course there's a parameter here, right? So actually if this holds for a particular n and arbitrary f, the corresponding operator is called, t is then called n positive. Right? And if it's true for all n, then this is called t is completely positive. Most of the time, we are not at all interested about in n positive operators that are not n plus 1 positive, except very special circumstances. So, I explained this only to tell you where this completely comes from. Right? So there is a definition n positive, which just says this, and if this is true for all n, we call it completely positive. So this is a requirement for operations on quantum systems that possibly can be executed on a subsystem. Okay, so why the fuss? Why am I making such a big fuss about this? Because it's not automatically true. Right? So I have to give you an example now of such an operation, which is positive. That is, it takes positive matrices to positive matrices. But when I tensor with an identity, it loses that property. And everybody who knows a little bit about quantum information knows exactly which example is coming now, right? Because there's only one obvious example here. So this whole explanation and this whole refinement is only necessary because actually it's not automatically true. This is a proper condition. Right? So let's do an example of a map T, which is positive, but not completely positive. So, okay, so let's just do the example. And so T is transposition. Okay, so let's just show why this is the case. First of all, if I have a positive matrix, so if A is positive, let's say, then T of A, or often also written just as A transpose, right, is also positive. How do I see that? Actually, positivity is a theme of the next chapter, where I give you all kinds of criteria, and then it would be very easy to do this. So I haven't really defined positivity, have I? Because I think you should have learned that in your quantum mechanics lecture, but for the moment, yeah, so A positive just means that so these are Hermitian matrices that have positive eigenvalues, right, or positive spectrum. We find a dimension here, so we can just talk about eigenvalues. Okay, so if I transpose such an operator, it's still Hermitian, right? Because I'm just exchanging the two indices. So transpose, so A transpose mu is defined as A mu. Just exchange those two indices. So hermiticity, write it out as an equation, and you see if I swap the names nu and mu somewhere, it still gives the same condition. Right? So the transpose of a Hermitian matrix is again Hermitian. Now the eigenvalues of a transpose operator are the same as the eigenvalues of the operator. Why? Write the characteristic equation, right? The determinant of A minus lambda. Now, the lambda is really lambda times the identity. So if I transpose under the determinant, I get the corresponding thing for the transpose operator. But the determinant of a transpose matrix is the same as the determinant of the matrix. Is that obvious for everybody? Yeah, I think it's obvious. So therefore, the eigenvalues will be the same. Right? And if they are all positive, they're actually the same eigenvalues. Right? So now let's apply T-tensor identity to an operator, to a suitable operator on a tensor product. You see here, in order to test that, we need to look at an operator on a tensor product. So choose H out as C2, so we have a qubit, and N equals 2. So actually that space up there is this C2 tensor C2, the very thing for which we wrote our those block matrix decompositions. Now, I will write my operator as in this form. I can always do that, right? So I use this expansion that I told you before. And then an identity tensor T, what does it do? This is the sum. Now, it doesn't change this part, so it will look exactly the same, at least the beginning of it. But then I operate with P on this F mu nu. So this is a very useful rule if you want to look at what does identity tensor T do to a tensor product operator. Well, in this block matrix decomposition, it will just operate separately on every block. Okay? So this is what's written here. Right? So it will operate on the blocks of B of H out, which is now also two-dimensional. So let me write a particular operator here, which is this one. Do you recognize what this does? So choose in particular. Right? So this is general, and this is in particular. What does this F do? The cats here are run over the whole basis, so this is still a sum over nu and mu. So basically you take all the components of a vector, and then you reinterpret which index belongs to which system. So actually, F is the flip operator that takes phi tensor psi into psi tensor phi. It just exchanges the two factors. Write it out, and you'll see that this is what it does. Or apply it. It suffices to check this on basis elements. Let's say on mu prime, tensor nu prime, and then you get deltas from this sum, and just the inverse order on the output. Right? So this is just a flip operator. Now, oh shit, I got the wrong one, huh? That's bad. No, I'm sorry. I made a mistake here. I want a positive operator. I want a positive operator. So actually, this is wrong. This will be the output, actually. Right, let me take this ordering of the indices. It's easy to get confused here. Okay, so what is that? So let's define a vector which is written like that. So it's E nu tensor E nu, right? And then you will recognize here that F is the Kepler combination of phi, and that is clearly positive. Right? So any such Kepler operator is positive. Is that? Should I check that again, or is that obvious enough? Right? If I write a scalar product around it, I just look at that diagonal matrix element. I just get the absolute square of the scalar product. Right? So this is a positive operator, but now if I apply int tensor F, int tensor T transpose to this, then it's good to use this formula explicitly. Then I get some mu nu tensor. Now I have to do the transpose of mu nu. Now the transpose, I told you this is the matrix that has a 1 in one place, namely the mu nu place, and a 0 otherwise. If I transpose that, I just exchange the rows and columns. So this is some mu nu tensor mu mu. So call this F prime or so. Now F prime is what I told you about. And this is not positive. Because if I apply F prime is this swap operator, and if I apply that to a vector, which is 1 over the square root of 2, just to keep it normal. No, let's drop that one. Remember, we are in 2 dimensions, right? And so these are basis vectors in 2 dimensions. In 4 dimensions, I mean, in the tensor product of 2 such factors. So 1 and 2 are the possible indices. And the only way to make an antisymmetric vector is this. Right? One that's antisymmetric with respect to the swapping of the 2 factors. So this is actually the only way to do that. And what you get is it will just exchange these 2 terms. So this is minus 1, 2, minus 2, 1. So it has an eigenvalue minus 1. So it's eigenvalue. Okay, so sorry for this little mix-up here. This is the positive operator, and if I apply the f prime, it will pick up a negative eigenvalue. Actually, this f can be written as a block matrix, and let me just do that because it's kind of instructive. So if you write this as a block matrix, so the vector has a component on 1, 1 and 2, 2. So if I make a ket bra out of that, so the ket bra phi psi gives the matrix psi 1, 1, psi 1, 1, psi 1, phi 1, psi 2 bar, and so on, and we get phi 2, psi 1 bar, and so on until phi 1 n psi n bar. So if you look at the matrix elements of such an operator, if you write that out as a matrix, you see that you have a product structure. So every entry is a product of one entry, one component from here, and the complex conjugate component from the other side. Right? And in the rows, the phi factor is constant, and in the columns, the psi part is constant. Right? So that's what a ket bra operator looks like as a matrix. So if I do it to this vector, I get 1, and I have my block matrix decomposition 1, 1, 1. All the rest is 0. Let me write little dots for 0. Not helpful, huh? I'll write small zeros anyway. So now this is a positive operator. It's a ket bra, right? So that's what I said before. I just want to make the contact to this principle that acting with identity tensor, a channel, is the same as acting on every block. So what does that do? Do we have color? Yes, we have color. Beautiful pink. So what does the transposition do? It doesn't do, so we have to apply transposition to every matrix block. Huh? Now, that is, we exchange these two guys, and we do this at every block. Now, on the diagonal, nothing happens, because there are zeros anyway that we are swapping here. But on the other ones, we swap this guy to the interior. Right? So actually, so actually what we get in this block matrix decomposition is 1, 1, 1, 1. So we have a 2 by 2 matrix block sitting in here. And otherwise, so we have a block decomposition into 3 blocks. Right? So everything that I didn't fill out is 0. So there's a 1, there's a 1, and there is this sigma x matrix sitting in the middle, which is just the matrix swapping 2 components, and that has a symmetric and an antisymmetric eigenvector. Right? And the antisymmetric one is the one that we picked up. 1, 2, and 2, 1 are the ones where the ordering of factors would produce an ambiguity if we didn't make a convention. I mentioned that before. So this is exactly the stuff that is swapped around here in this operation of the transpose. Okay, are there questions about that? So let me mention how other examples that are in some sense the same example. So if you do quantum field theory, then you probably have heard about the PCT theorem. So those are discrete symmetries of quantum field theory. P is the parity, that is space inversion. C is charge conjugation, and T is time reversal. Now, time reversal is something that can only be a symmetry if it's implemented in an anti-unitary way, because otherwise positive energy would be swapped to negative energy, and energy just happens to be positive, right? So the only way to implement time reversal is by an anti-unitary symmetry. So that is, instead of writing, so A goes to U star AU, we write A goes to U star A star U. For Hermitian elements, that's the same, right? So you can forget the one star. But the U would be an operator that is anti-unitary. Now, anti-unitary is not the opposite of unitary. It just means that it's unitary, but scalar factors are pulled through with a complex conjugation. So if I act with an anti-unitary operator on a vector and multiply that vector by I get minus I times the operator, right? So that the anti is, I think the better term would be conjugate unitary or conjugate linear unitary. And there's a famous theorem, Wigner's theorem, that you may have heard about in your quantum mechanics lecture, that tells you that every symmetry of quantum mechanics, that is, every symmetry of the state space, we'll come to that in a second, is implemented by a unitary or an anti-unitary operator. So actually, complex conjugation is very much a symmetry of, in that sense, of Wigner. Right? So it is a symmetry in the same way that time reversal and charge conjugation are symmetries of the world, as quantum field theory knows it. Right? So how does this match? Right? So anti-unitary. So the principle here is that not just transposition. Transposition actually comes by this conjugation, where the unitary operator is just complex conjugation. This is an anti-unitary operator. So if you have an Hermitian matrix and you write complex conjugation before and after it, what really happens is that you again have a Hermitian matrix, but the matrix elements are complex conjugated. For a Hermitian matrix, that's the same as transposition, right? Because if you do both together, you get the same thing. So this is really an anti-unitarily implemented operation. It's a symmetry in the sense of Wigner. And yet we say, we don't want this. In quantum information, we don't want to work with that. So the reason being that if we apply, that's what we proved here, right? So if we apply this kind of anti-unitary symmetry to a subsystem, it will create problems. Namely, something that was a decently prepared positive state, like this guy, will turn out to be not positive after the operation to a subsystem. So there are certain symmetries that may be symmetries of the whole world, like time reversal, but if I try to do a time reversal on a subsystem, I get problems. That's what we just showed. Right? And for quantum information, it's crucial to have this possibility to operate on a subsystem. We are not that ambitious. Quantum field theorists are ambitious. They describe the whole world. Quantum information people want to talk about the quantum computer in their lab and would allow the rest of the world to exist. Right? So it's always a theory of a subsystem. So we have to be picky about that. Right? And so these anti-unitary symmetries are excluded. Okay, so here's another little way of looking at it. You have the Bloch sphere as the simplest system ever. Right? Transposition is the same as implementing complex conjugation. Or let's look at it in another way. The Bloch sphere comes by expanding your density operator in Pauli matrices. And those are the components are the three coordinates. Right? Now, of the Pauli matrices, sigma 3 and sigma x are symmetric. They don't change under transposition. Right? Sigma x has, how do I have to show this? like this, no, like that, right? On the off diagonals, I have 1s, and if I swap those, nothing happens. But sigma 2, or sigma y, as it's called in some places, has iy and minus iy and I on the off diagonal. So if you swap that, you get a minus sign. So actually, the action of transposition on the Bloch sphere is reflecting, changing the sign of the second coordinate. Well, okay, this is 1, 2, 3. Okay, so 1, 2. So the plane vertical, this vertical plane, at this vertical plane, I do a mirror image. So this is an operation that is a symmetry of the sphere. Right? It's a mapping on the sphere that is reversible. Actually, it just has square 1. Right? So it's clearly it's a symmetry operation, but it doesn't satisfy this condition. Actually, there's another one that is bad. And actually, this is classified by the sign that is the square of this anti-unitary operator. If you multiply an anti-unitary involution with itself, that is, involution just means that as an operation on the state space, doing it twice takes you back to the original, right? So it's clearly this reflection at a plane, that's the kind of transposition operation, right? So this is positive. It maps the full state space to the full state space, so it clearly must be positive. But it's not completely positive. Now, there's one reflection that is okay. Namely, that is the reflection at a line. So let's say take the vertical axis, and I reflect at the line. That is, I take, for every point, I go horizontally through the polar axis of the sphere, and go the same distance to the other direction, right? So this is a reflection at a line. Why is this positive? Well, I can do this by rotating around that axis by an angle pi, right? So in 2 dimensions, reflection at the origin is actually a rotation, namely a rotation by 180 degrees. So that must be completely positive. So this is, and it certainly is. So there's one more possibility, and that is implemented by an anti-unitary that squares to -1, and that is the reflection at the origin. This is called the universal not operation. That is, it takes every qubit, every pure qubit state, and maps it to another pure qubit state, which is, those would be the ones on the periphery, which is orthogonal to it. So it not only takes the up state to the down state, but it does so in every basis. So this is called the universal not, and it's just as forbidden as a transposition. Right? That's another sort of involution that is not completely positive. Okay, so let's go to the positive side, or the completely positive side rather, and do some examples of channels that satisfy these conditions. Of course, most of the time we'll just happily have completely positive things. So let's do some examples of channels. So let's say unitary ones. Well, to be very picky, I should let's put the quotes here. A better term would be unitarily implemented. So depending how many minutes I have to go, I might say just a unitary channel when I mean a unitarily implemented one. And that just means that T of A is U star A, U with U unitary. By the way, the Schrödinger picture for that, T star rho, will then be U rho, U Q star, as you can very quickly compute by using the cyclicity of the trace. Okay, so this, for example, the time evolution would do that. Right? And those are really the symmetries. Actually, this is equivalent to T has an inverse. Has a two-sided inverse, let's say. Actually, I said that the Hilbert space can change. Now, for unitary operators, I also use some unitary operators that map between different spaces. And in the same spirit, this could change the space that we're working on. So H in and H out could be different. In general. Okay. Now, why is that? I'll postpone the checking that this is completely positive. But this that if you know that this operation is positive, well, then that's easy to check. Actually, we'll do that explicitly later, anyhow. So that's easy to see. So if you identity tensor T is of the very same form where you just take unit operator tensor U as the implementing unitary. Right? So then this immediately shows that it's completely positive. So, but we'll come to that. So what were my other examples? Depolarizing. So these are things that I write this in the Schrödinger picture. So mu here is you can think of mu as a probability, and so what this does is, it either, with the probability mu, the system is unchanged, or with probability 1 minus mu, it's replaced by this guy. Okay? Very easy. So that's how you would do this channel. Now, nobody usually does that in the lab, because this is just messing up something that they have carefully prepared. Like the row probably cost you a few $1,000s, euros. And so just throwing it away some of the time is usually a silly operation. However, this is a good description of what noise might actually do to your system. So then if you have a noisy environment, then with a certain fraction of instances, it might happen that your state gets messed up. And this is a very simple noise model. There's more complicated kinds of noise, but this is certainly a simple kind of noise. Another thing that doesn't immediately meet the eye if you look at this expression and think of mu as a probability is so if rho naught is 1/2 the identity on a 2x2 system, so it's the center of the Bloch sphere. Right? Rho naught would be the center of the Bloch sphere, then everything is sort of contracted to the Bloch sphere. And now if I take mu equal -1, yes, mu equal -1, then T star is the universal knot that I just described. So this is not completely positive. So if I change mu around, it's fairly obvious, then I might get something that is not completely positive. But on that scale, on this one-dimensional line of transformations, I get this universal knot, which is positive, but not completely positive. Right? It will actually map everything to its reflection at the origin. Okay, so the but mu equal minus, let me write a fantasy number 42 over 137 or so. This means also. Is still CP. Actually, I forgot to say that completely positive is such an awfully long word. So CP is actually a lot of the time the jargon. So if I write CP on the board, it always means completely positive. And even if I say CP, that's what it means. Right? So, so actually there's a critical value, which is negative though. So you sort of over depolarize. You take the Bloch sphere and sort of invert it, but only partially. And that is still a completely positive operation. I computed that number in the late 90s. Right? And there's a little paper with Vlado Buzek about this. Okay, but this is just a warning to say that this can be a parameter that is different from an actual probability. Right? For positive mu, I can clearly implement it in the way I described. For negative mu, you have to do something else. Right? Okay, so what else do I have on my list? For Neumann measurement. So I picked some basis, and because I'm only looking at one basis, I'll just use that notation, that shorthand notation. Also for the basis Ketbra, so these are the projections onto the basis vectors. So this is an orthogonal family of one-dimensional projections, and I can look at actually computing the Heisenberg picture for that and stuff like this is a good set of exercises of the simple kind to just let you recap what is going on. So again, I write this in the Schrödinger picture. So what this does is now pi is a basis, and each such vector has only a matrix element in the II place. Right? That's what this projection does. So, and the matrix element there is exactly rho II. So what this operation does is project onto the diagonal. It kills all the off-diagonal elements. Now, there is an interpretation of this, which is for Neumann's projection postulate. Namely, it says that you learned in your quantum mechanics course, probably, that if you make a measurement of an observable A, now these are the eigen projections of the observable A, then the outcome is going to be an eigenvalue, and conditional on a particular eigenvalue coming out of the measurement, the state after the measurement is going to be the eigenstate. And this is exactly what happens here. So there is, this term has a probability of actually the result I occurring, and this is just proportional to pi. If this is a one-dimensional projector, this is just a number, namely rho II times pi. Right? So with this probability, you get the eigenstate afterwards. So von Neumann wrote this down because it satisfied his quantum logical instincts, and we still this is all over the textbooks. But actually, and some measurements are actually like that. So this is a possible description of a measurement, including the state after the measurement. Right? If you just have an observable, the system could have been destroyed. You don't care what the system does afterwards. It's no longer available, so you can't make any measurements. on it anymore, so aus den Augen, aus dem Sinn. I don't know how to say that in English. So that's gone. But this, in some cases, you do want to describe the state after the measurement. This is one example of how to do that. We'll talk about measurement theory in more detail. So I have just one more example, but the blackboard is full and the time is almost up. So I'll do this next Wednesday after Easter. So I wish you all a happy Easter, and we'll think a little bit about nice problems, not difficult ones, but ones where you can learn something. Yeah, okay.
Yeah, like back to this Heisenberg and Schrödinger picture.
Yes.
Maybe it's a stupid question, but what if I have like interaction picture or something like this?
Yeah, well, the interaction picture is sort of an intermediate way, right? Which has some usefulness in time-dependent perturbation theory, as you know. I don't think it's on the same kind of fundamental level as the other two. Right? Of course, you could kind of split you could have a transformation on both ends, and but this is really just a way of extracting one kind of time evolution as trivial, and then looking at the rest in your series expansion. Right? So I don't think it has the same kind of fundamental status as Heisenberg and Schrödinger.
How do I even draw it? I mean, I cannot draw two channels because they kind of interact or something.
Sorry?
I cannot draw just two channels because the trivial dynamics and the perturbation kind of...
Yeah, I could use channel boxes for that. I did for the trivial dynamics, right? So any kind of weighting operation is a good box. But then both parts are time dependent, and I think the best way to think about it is just as a way of, I would actually write the Dyson series without explicitly introducing the interaction picture. I think this can be eliminated from textbooks without any loss. It doesn't do anything for you. But that's a matter of taste again. I mean, if somebody wants to use it, fine. But I don't think it has this fundamental status, and it is actually expendable. You just get rid of one factor ut somehow, right? And if you're happy with keeping that in there, your interaction picture, Dyson expansion becomes a Schrödinger or Heisenberg picture, Dyson expansion. So I don't think it really does a lot of work in perturbation theory. But anyway, that's, as I said, it's a matter of taste. Okay. Any more questions? So I'll see you on Wednesday.